the traction vessel at the head of the train. The fuel costs for this system are in fact lower than one would find on a tanker system. Another advantage has to do with redundancy. The seasnake traction unit, as we said earlier, is at the head of the train, but it is also possible to station a second traction unit at the stern, or the last unit in the train. That would be a traction barge. That traction barge could act as a take-home unit or as a secondary power unit in the event that there were problems with the lead traction unit. Furthermore, that trailing traction unit could function as a pickup and delivery unit that would permit the delivery of individual barges to terminals while the mothership was at anchor or was at another facility.
The seasnake barges are unmanned, thereby reducing the cost of labor. The power requirement is slightly less than in a conventional tanker, and greatly less than in an integrated tug barge system, which is weather restricted. The individual, disconnected barges have a length of 260 feet, as compared to 890 feet for a 130,000-ton tanker, thus reducing required dock space. The loss in downtime for periodic maintenance is eliminated. The units are sent to maintenance and replaced on a rotational schedule. The time loss in loading and unloading is reduced to a fraction of what it is at present. The drop-and-swap method of delivery ensures short turnaround time. The barges are self-loading. Each of the barges carries its own pumping equipment. The individual units of the seasnake concept are safer in case of collision. In the event of a collision, the damage will most likely be restricted to only one barge. The damaged unit is simply disconnected and removed, and you do not lose the entire ship. It is also safer in case of fire. The burning module can be quickly isolated by the quick disconnect mechanism. As a safety precaution, the seasnake concept provides for redundancy in the power supply. In the case of a power failure in the traction unit, the rear unit takes over. The versatility of the seasnake concept is evident in that the size of the ship, the number of units in the train, is adjusted to the commercial needs of the carrier. The same ship is used for the delivery of 300,000 tons through the open sea, as for the delivery of 43,000 to a destination requiring a smaller amount of cargo. The individual barges of the seasnake can act as temporary floating storage tanks in harbors or at the base of offshore drilling rigs. In the case of a collision where a tank is ruptured, the oil spill in a 200,000-ton tanker would be 17,000 tons. If the ship is lost, the potential for the spill could be far greater. On the other hand, in the case of a collision with a seasnake SS-45 barge, the spill from a ruptured tank would only be 2,200 tons, or 8 times less than that of a conventional supertanker. The history of the seasnake concept spans more than a quarter century and was the brainchild of a mechanical engineer by the name of Karl Kuntz. The question of shipping oil from Mexican ports was of great interest to Mr. Kuntz. The problem was that the draft of the harbors in the Gulf of Mexico was too low to accommodate the large tankers that were being built at that time. Mr. Kuntz conceived the idea of a modular ship that would retain the advantages of the large tankers and eliminate their disadvantages. He started to prepare a technical analysis which convinced him of the feasibility of the concept. However, the magnitude of the project was overwhelming and was shelved. In 1992, Mr. Kuntz met his present associate, John F. Markley, who actively encouraged Mr. Kuntz to revive his project and to apply for a patent. Karl Kuntz prepared a formal feasibility study and submitted it for evaluation to C.R. Cushing & Company, an established naval architect and marine engineering firm in New York City. In September 1999, they finished their report with a favorable outcome. Karl then made some refinements and adjustments to his design. In January 2001, The Advanced Analysis Department of the ABS undertook a computer analysis to determine the wave-induced forces acting on the hull and the connection system.
American Bureau of Shipping, established in 1862, is a classification society. It is primarily a marine regulatory body involved with the development and establishment of rules for the building of structures and facilities in the maritime and offshore industry. Seasnake wanted us to perform an approval of the design. However, seasnake concept does fall outside most ABS rules and guidance. In such cases, ABS would perform a direct independent analysis of the concept so that we can establish the limits of operation of the design, which is further used by the designer to carry out detailed design of the structure and then follow up with submittal of the design for approval by ABS. So our role, advanced analysis role in this, was to perform the initial independent direct analysis. The direct analysis usually starts off with what we call a seakeeping analysis. The seakeeping analysis is something where you would actually model the vessel performing motions in waves so that you can actually predict the level of motions and the associated loads on the hull. Because Seasnake came to us and wanted to perform an assessment of the design's feasibility for service in unrestricted ocean conditions, and which would be what we would do for a large ship, ocean-going ship. These tests are what we call numerical modeling. This involves modeling the shape of the hull, its mass or weight characteristics, as well as any appendages that are attached to the hull. And the motion analysis involves calculating the forces on the hull due to the imposed waves on them, and the analysis produces the motions as well as the loads acting on the hull simultaneously. The result of this would be in the form of external pressures on the hull, which could then be mapped onto a finite element model, which is normally used for detailed structural analysis. The results of the tests consisted of, as I mentioned earlier, all the 6 degree of freedom motions of the vessel, the load effect parameters such as bending moment. Bending moment is a parameter which is critical in the design of all structures. That, along with the reactions at the connectors between these barges, form a set of results that came out of our analysis. And that is further used by the designer to produce a detailed structural design.